mycelium could be like when you have a specific species of mycelium or mycelium that is bioengineered to have high melanin content, then it can provide radiation protection capabilities. So it would be really amazing if you can just deploy the habitat and it already provides radiation protection for astronauts.
We're shooting today from Calgary, Canada, during the International Conference for Environmental Systems in their 52nd session. A PhD researcher at the Hub for Biotechnology in the Built Environment and the NASA Ames Center, you design habitats for inhabitable environments for the planet Earth and beyond. Your research attempts to answer questions that challenge the stereotypical assumptions of what we already think we know. And you basically push the boundary of known assumptions and default constraints. Your research and passion focuses on assessing biotechnologies and biomaterials to sustain human habitats in extreme and extraterrestrial environments. For example, your master thesis project was about nanocellulose application in radiation shielding architecture. So today we have you here, Monika, with us. Welcome.
Thank you. Thank you for having me.
Thank you so much for taking the time to speak about your research. I want to introduce, before we get into the research that we're here to discuss, tell us more about yourself and how did you start thinking about biomaterials to construct in space?
So I was studying architecture as my first field of studies, but I always knew that I will somehow find my way within it, because I'm coming from a family of architects. My grandpa was an architect, my parents are architects, so it was kind of natural thing for me to go for architecture, but I knew that I'll find something for me. I didn't know what that is, and I wasn't really actively looking for it. I just kind of knew that it will somehow appear and I'll have this enlightenment that this is what I want to do. And at some point it came to me with space architecture. So space architecture was before biology, let's say. I started working with, I found this space architecture competition, or my friends sent it to me actually after I started publicly telling everyone that I want to do space architecture. And then I chose my master's studies based on the fact that I wanted to do something towards space. And then when I was doing my master thesis, I was designing this lunar habitat, and that's when I started looking for different materials. I don't remember exactly the point where I started working with biological materials. It just somehow came to me with the nanocellulose. I think some research institute, I was studying in Sweden, and there was some research institute that was offering internships with innovative materials and nanocellulose, and that's where I got interested in that because I didn't know what it is. And then when I read about it, I had this idea of applying to space architecture and use it as a part of construction system for lunar habitat. But back then I didn't have any expertise in biology. My studies in architecture was really cool because it was the specialization in spatial experiments, so it was a lot of bottom-up approach, extreme environments, additive manufacturing. So we weren't designing regular, let's say, buildings. It was very experimental, and they were very open for the fact that I wanted to do space architecture, so they just let me do whatever I want. But I was lacking this expertise in biology, so I made this project, but it was very much theoretical, and I just, what I read, I put in the project, kind of. And then I went for International Space University to get more background in space in general and how to work within space industry with other disciplines. And that's where I got opportunity to do my internships at NASA. And it's really funny because my internships at NASA, it was at the astrobiology lab, but at Lynn Rothschild astrobiology lab, whom I met a couple of years before on this conference, Tarmus, in Norway. She was the first person from NASA that I saw in my life, real in person. So I was super excited. But she had this amazing energy. She was not talking about architecture. She was talking about the most extreme places on Earth where we can find life, and then how to push this life to the more extremes. So if we find exoplanets, we can assess if it's possible to find life there. So it was not connected to architecture at all. But she had this amazing energy, so I built my courage over the week to go to talk to her. And then at some point, we were on this walk in Trondheim, and then she talked to herself, maybe I need people like you in my astrobiology lab at NASA. And I was like, oh my God, did she just say that they need me at NASA? So then when I had opportunity to actually formally do internships at NASA, then I contacted her. And at that time, she was working on microarchitecture projects, so she actually had architecture projects. So it felt like it's all was meant to be, and I joined her group. And that's where I was suddenly the only architect working in astrobiology. So it was always something weird. I was either doing space with an architect or biology in space. It was always something that was a bit different. But then now with my PhD at Hub for Biotechnology in Built Environment and collaborating with NASA, it kind of all merged together into biospace architecture.
That's amazing, because the first thing I would think about when we think about space architecture is trying to make a space that has no known biology thriving and could help us build the habitats. So it's good that you had that forward thinking, because otherwise people would just listen to the idea and say, oh, it's never going to work. So glad you pushed the boundary on this.
Yeah, and I think what's really cool is to at this astrobiology lab at NASA, for example, I was very open with the fact that I don't have any biological experience, any expertise. I don't know anything other than high school level of biology. So I was very open with asking questions, and even if it was the most basic things, I was just I let myself not know it. And from that discussions where I was very open with what about this, or why we didn't consider this, or is this possible? Because I don't know, maybe it is, maybe it's not. It was generating a lot of cool ideas. So yeah, I think this meeting different disciplines and being very open with the fact that you might not know things, it's really cool when you combine.
I think this is not advocacy for architecture, but I feel like it's one of those disciplines that when you study it, it gives you a perspective on everybody else. Yeah. Because the architect is the person that brings everybody else. So you don't need to be an expert in mechanical systems. You need to know enough, so that you can make them happy, and you make the electrical engineers happy, and you make everybody happy while still being creative and doing things outside of what they think is the default way to do things.
Yeah, no, I definitely agree. But it also makes you sometimes lose the focus, because you read about something super interesting and you already have these ideas of how you might use it, and then I was finding myself reading about molecular structure and synthetic biology on the nanocellulose, which is not that relevant for architecture, but you go deeper and deeper and deeper because you want to understand it. So sometimes it's easy to get lost in how much you actually need to understand versus how much you want to understand. But yeah, definitely you have to you're the person that combines those fields and kind of translates between different disciplines, I think, also, because the matter of vocabulary and language, it's a big, I wouldn't say barrier, but it's something that in architecture and biology, for example, you have the same words that mean exactly different things. Scaffolding in biology and scaffolding in architecture are completely different things on different scales. So it's also important to have in mind that the language is to navigate.
In some way they are different things because of different scales and different contexts, but they're also similar. It's one of those things where it's a thin line of how you can think about them. So you're here today because in the conference, because you presented your peer-reviewed research, which is Drop the Base, biological ISRU-based aleatory construction system for Martian habitat. So in other words, you're doing in situ grown mycelium-based regolith composites. And even in better, more simpler terms, you're using fungus or species of fungus to build habitats for Mars.
Yeah, it's correct, because like fungus is the overall thing, and then fungus has a fungi and it has mycelium, and I'm using mycelium, but like in the end it's all part of fungus, I guess. So, yeah,
tell us more
correct.
about this and walk us through it.
So the idea is that, so this is the project that I started working on with Lynn Rothschild at NASA during my internships a couple of years ago. The idea is to use mycelium, which is this vegetative part of fungi, mushroom. So like the branching structure of the fungi, to grow, to make habitats on Moon or Mars. At first the project was for Mars, then with NASA Artemis plans, the focus shifted on the Moon. But then within that project, I started continuing it as my PhD research, so I had to find my own path, let's say, which is still part of this microarchitecture. It's NASA NIAC funded project, so it's NASA Institute of Advanced Concepts. So for my PhD research, I had to find my own path, so it's original research, so I can work on it as my PhD research, but it's part of the NASA NIAC. So the NASA approach is to use mycelium to create myco-shell, let's say. So the idea is that you take this deployable, inflatable structure that is made on Earth, and it's preceded with algae and or cyanobacteria and mycelium to a certain level, and then we take it to Moon or Mars. Mars makes a little bit more sense in a way that the idea is that you deploy it on the surface, and then you add water, sunlight, and carbon dioxide, which is present in Martian atmosphere. That's why it makes more sense for Mars, that specific approach, but it could also work on the Moon. So you add water, carbon dioxide, and sunlight, and then cyanobacteria and algae start feeding on that and start growing, and then they produce oxygen and they produce nutritional mass. And then after they are fully grown, the mycelium starts feeding on it, because mycelium need oxygen and it needs nutrition, and that starts feeding on it, and it consolidates the organic matter and creates this consolidated myco-shell. Because mycelium feeds on any kind of organic substrates, it secretes enzymes and like bind the structure together. On Earth, it's used for many like architectural installations, also as insulation for architecture or for packaging. So it's very lightweight, fire resistance, acoustic material. But the beauty of it in space exploration is that it self-replicates and it's self-healing. So you can take just a little bit with you and then repopulate it directly at the destination. So that's NASA's approach, that like you have this preceded bag and everything happens in a closed environment of that deployable habitat.
So basically what the concept that you started off with is that you will have this inflatable habitat, it will be deployed on the Martian surface, and within that habitat you will start the process of using this as to build the...
So it's like it's all preceded, and the inflatable is kind of made out of separate compartments, and each compartment is preceded with algae and cyanobacteria, and then after you add water and carbon dioxide and sunlight, that grows, but that grows within this inflated compartments, and then mycelium feeds on it, and you have this myco-shell habitat, and that's for Mars or for the Moon. Mycelium could be like when you have a specific species of mycelium or mycelium that is bioengineered to have high melanin content, then it can provide radiation protection capabilities. So it would be really amazing if you can just deploy the habitat and it already provides radiation protection for astronauts. Unfortunately, we're not able to say that the radiation protection that fungi can give is enough to protect astronauts. So in the end, it might have to be necessary to cover this deployed habitat with the layer of regolith anyways. Also, the internal pressure between inside and the outside could be too big, so you still have to like use regolith to cover it so it doesn't burst. So for my research, for my PhD project, I decided to look into combination of mycelium with regolith in the first place, since it might have to be necessary to use it anyways. And I started with basically very basic research into how to grow mycelium on inorganic aggregate, because normally it's used on organic substrates, so like coffee grains or beetroot, sawdust, hemp, anything that's organic that mycelium can feed on. So I'm looking into how can we minimize this organic part, because we don't have beetroot on Mars. We will have greenhouse, and potentially we could use greenhouse waste and like non-edible parts of plants, or even like human waste, so anything that's organic. But I'm looking into how to minimize that, so mycelium can still grows, but it acts as this binder for regolith, and it like binds the regolith, so you can replicate it on site. Regolith is there
as an agent. It's a binding agent.
Yeah, basically. So like it literally, like I started with petri dish experiments, and then under the microscope you could see that mycelium, this thread of mycelium, they literally hold grains of sand, like they just hold it. And then I have these columns, and you can really see that it works in the sense that the mycelium binds the sand. I'm working for now with sand, so there's still a lot of research to figure it out how to do it on the regolith, because of the grain size, because of the chemical compositions, toxicity. But on the other hand, mycelium has the properties to like detoxify soil, so that could be also a first step towards using regolith, that mycelium would detoxify it somehow. But there's a lot of research when it comes to like finding proper nutrients that could be available at destination that mycelium can feed on, which mycelium species to use. So yeah, there's still a lot to do. I'm working with like, is it possible to grow it?
But it's possibility that it is a good foundation for maybe it will happen. It's like the first indicators. It sounds like it's checking lots of the boxes that we want. Yes, there are questions, but we're still able to see kind of the possibility of it. Right?
Yeah. And also, like, it's not that one technology is instead of the other. In the end, it will be this like palette of materials that, for depending on the application that you need, you can use solar sintering, and some other parts of the habitat you use mycelium if you want more haptic surfaces, for example, because it has this organic feel, so it could be good for astronaut psychological comfort. It could also perform in the long run like biosensing. You can have mycelium-based electronics, so you can have the habitat where, like, as we build houses here on Earth, that the different parts of the building are built in different ways and from different materials. The same way, like, looking at the innovative and novel materials for space application gives us this variety of what we can do there.
Yeah, I agree. And from most of the projects, especially like the student projects that are being proposed, it feels like to me assumed to be using one material. And you're right, it's going to be a hybrid of different things depending on the application or depending on the use. Okay, so for the mycelium that we're talking about here, is it going to be active all the time, or is there a time where it has to stop being active?
Yeah, so in the project that I'm developing, the idea is that you make components, so kind of like bricks of certain geometry. They're made out of mycelium, so mycelium is alive during the growth within the regolith, and then consolidates the components. But it's kept alive, so the components later on, they're assembled together, and that's another part of my research. Is I'm specifically looking into resource-limited Martian conditions. So one thing is minimize nutrients, the other thing is to have construction system that could be with minimum intervention. So maybe not necessarily self-assembly, but semi-self-assembly, something that we don't need precise robotic operations and put brick by brick with mortar and build it, but something more that you drop it, that hence the name of the project, you drop the components and they assemble together, or you push them somehow. So you don't need this precise operations, you can just put it together and through the geometry they assemble into the habitat, the shape of the habitat. But because the components are alive, they can perform bio-welding. So it's like a biological fusion where this biological matter in the component, mycelium, tends to grow within each other, and then the bricks are consolidated into one whole consistent structure. It could be even sealed environment, but I wouldn't go that far with predictions. It's probably better to still have this like core of the habitat, providing life support systems brought from Earth, like that you're absolutely sure that it's pressurized and sealed, but like to provide radiation protection and in general shell structure, we could use this mycelium that bio-welds. The other thing is that mycelium won't be possible to be grown in Martian conditions because of the temperature and pressure. So we would need anyway some kind of closed environment where we can grow these components. But on the other hand, even if it would be possible to grow mycelium, we cannot really grow it on the open space Mars because of the planetary protection. So there is like, I'm not specifically working at this, like I'm not solving that challenge yet. I'm having it somewhere in the back of my head that would have to be somehow solved in like a long-term like roadmap of how the whole construction process would look like, and you need to deploy something, and then the external part of the habitat could be killed, because killing the mycelium doesn't lower the properties, like the structural properties of mycelium. The way how it's used on Earth, it's actually baked, so mycelium is killed, so it doesn't grow further, because if you keep it on organic substrate, it would just keep digesting it, and then you lose structural properties. So you have to kill it. If we grow it on sand or like regolith, then mycelium wouldn't digest that. So I hope that the structural property stays, and then we can keep mycelium alive to perform functions like biosensing and mycelium-based electronics, or in certain parts of the habitat it can be producing food, producing mushrooms. In the other parts of the habitat it can digest waste. So you can have this like living habitation system where you can keep mycelium alive because the structural part is provided by sand. On the other hand, from the outside it could be killed, so there's no it's not exposed to Martian conditions. The question is how it is killed. Is it enough that we somehow expose it and we know that the Martian environment kills it, or that's too risky because like maybe
degrades it?
Yeah, so
it's time and dust.
The question is if it's safe enough to, even if we can assume that Martian environments kills mycelium, is our assumption enough for planetary protection perspective? Because if you open it and somehow this mycelium will survive, then we contaminate Mars with mycelium. So I don't really know, and I think there is no like proper answer yet of how to do it. There are a lot of like plans of how planetary protection should be handled for first Mars mission, but that's not including any biological biotechnologies, biomining. But we have all of that in plans, right? Like biomining, for example, it's something that we're not planning to keep it in closed environment. The goal of it is that we're using biological material to extract metals from the regolith. So there is direct contact of bio and Mars. So I don't really know. I don't really have answers for that. And yeah, it's definitely a challenge. It's something that we have to think about step by step.
It is, yeah. And I would completely understand if there are more questions than answers. And this is what's interesting, is that you keep finding the questions and then working through them as you go. Mike, so the question would be, I know that all of the projects and what's being sent to Mars is trying to keep in mind that we do not want to contaminate, whether for various reasons. You don't want to contaminate the Martian surface. One is ethical, because who are we to colonize something that may have already owners or life on it, whether it's bacteria or anything else. But the other scientific question is that we don't want to contaminate, so that in the future, if we find something, we want to know if it's us or is theirs. So it's hard to think about this. But I feel like, at which point do you think that a project like this is somehow like a breaking of the glass? Like it's inevitable that we will have to do this, despite all of the other questions.
I think as soon as we have humans going to Mars, it doesn't really, like, we still have to think about planetary protection, but we are, with humans, we're bringing billions of bacteria, right? Like, we have billions of bacteria on ourselves. So it's not that we can just be, completely forget about planetary protection and do whatever we want. We still have to think about it. But my reasoning is, if humans are going there, we're kind of agreeing on bringing biological life to Mars. So we just have to find a way to, not contaminate it. I was talking yesterday with planetary protection expert, and she couldn't give me specific answers of how to do it. I asked her at some point, like, what if we find life there? If we find life, is then there no go to Mars? And she said, no, I think then we will start going even more, because it will be even more interesting. But like, we have to know how to handle it, and then maybe there will be like regions of Mars that are like absolutely like, we're not going there because there is bigger possibility to find life. But we want to explore, so like, I guess if humans are going there, we can use biology, but of course not, without thinking. Just like, we cannot make forest on Mars, because we cannot. But even if we could, like, we wouldn't do it.
Yeah,
I guess.
But
we want to go there. Yeah. So yeah, I don't really have answers for that. It's very. You said also, like, it's ethical matter as well. So.
And so for the habitats that you're imagining, how would be the concept of operations? Is it something that we will send, wait, and then we will send the astronauts? Is it something that we have to send humans to help us do it? Does it require robots? Like, what do you think? You imagine the most plausible, most rational scenario?
I don't have like one scenario on my mind that like I'm targeting for that. I wouldn't say that it's the most reliable at this point technology, because it's a research of how to grow mycelium on sand. So it's very, very early technology development. So it's more like just to check what are the options. We definitely need organic matter to grow mycelium. So it either could be that we have a greenhouse, or like, I don't know, a mission that goes before humans go, just to make sure that the whole habitat is set, and I don't know, greenhouse is operating for, I don't know how much to say it's reliable, a couple of months, a year, and then we can send humans, and then we would already have biological material, so we can start growing parts of the habitats. But I wouldn't say that it's something that it's completely autonomous, send before humans, and then the habitat grows, and then we can send humans there. Because I think it's more something that could be developed while humans are there for like future missions, because you can grow it, you can like adapt it for future mission needs, for future, like, I don't know, we have more astronauts, or the concept of the mission changes, and you need different parts of the habitat, and then like you have possibility to, instead of bringing new modules throughout the time, you can just plan ahead and grow more structures. I see it more like that. So not like absolute, like, reliable habitat waiting for first humans to arrive, but rather it's like fun thing to do while you're there, and you can just grow more habitat.
I'm also imagining there would be maybe a scenario where we would send one of those deployable, inflatable habitats where the mycelium, even if it's a small one, until we send humans and see how it behaves.
Exactly. But I wouldn't say it's the only thing that it's, if that doesn't work, then the mission fails. Like, but I guess none of the technologies should be, should have 100% trust in their reliability that they send just one option. I guess it should be always at least, I don't know, 2 or 3 backups in case something doesn't work, and then we try something else. I hope it works this way.
And all of the testing and experiments you have for the mycelium, they were in control. Like, what kind of environments you used to cultivate this?
Yeah, so I'm working in this growing chamber that we have available. So it's not really like, I'm not really targeting Martian environment at this point. I was thinking of maybe trying to grow mycelium in lower pressure, just to see like what would be the minimum pressure of mycelium to grow, or lower temperatures. But in the end, I'm not looking into that. So I'm working in the regular Earth environment, the same way as other mycelium-based components are developed on Earth. So it's temperature,
at a macro
like,
level. you're working on a macro level now, and not going yet into the, like you said, a pressure. Like it's just a question. Like, is it considered you want to validate the overall hypothesis?
Yeah. So yeah, exactly. So I want to see. So what I already accomplished is I know that mycelium can be a binding agent for the inorganic substrate, inorganic aggregate. So it's not specifically regolith. I have regolith simulants from Lynn Rothschild actually to grow mycelium on that and see how it works. But in the scale that I'm working right now, I'm working with sand because it's so much more of the material. So that's why I'm working with sand, because like I'm growing different samples with different levels of nutrients, so biomass versus inorganic matter. I see it works. I'm not sure. I don't have yet completely like optimized recipe of like this much water, this much to have the optimal strength of the sample. So that's where I am right now. Like I'm redoing experiments, I'm redoing and trying to find like optimal growth conditions and recipe. But I'm still working like earth conditions, if that makes sense. Like regular, like 20, 25 degrees Celsius temperature, hour pressure.
Do you think that the earth environment and the conditions, they are like for something that will grow in space and will have to be killed? I hope I will phrase this question properly. Do you think that if it survived and you were able to validate lots of the assumptions in an earth environment, do you think it's one of those areas where it might be easier in an environment where there's no oxygen, there's low pressure? Like you think that in this condition, is the earth environment more constraining?
Yeah, I see your point. I'm very curious how mycelium grows in lower gravity conditions. I don't know that, and I don't know how to predict it, like maybe based on like biological research on plants, but I'm really curious how would that work. So here I'm not sure. Maybe it would help mycelium to grow, especially like in the samples that are bigger in the size. Maybe like it's easier to grow inside because there is not that much, even if you have dense structure, there's not that much load on the mycelium inside or like on the bottom of the sample. On Earth it could be struggling because it's like too dense, and Mars or on the moon it could grow easier, but I don't know that. Other the growth factors, I think they are much more challenging. So that's why we need this enclosed environment to provide like proper temperature and proper pressure. So here I think it's more challenging. But from the assembly point of view, here it's again where lower gravity conditions can be beneficial for like dropping the components or pushing the components, where like you can drop something from much bigger height or of a bigger mass and it just doesn't break that easily because the gravity is lower. So I really hope the Martian or lunar environment will help with the assembly process. But the growth itself, I'm not sure.
And I'm curious, like with this experiments that you did, what is the life cycle like for like the mycelium to grow into relatively like a small structure? Like, is there a linear correlation between the time and the scale of
I wouldn't say the scale, because you need like mycelium needs oxygen to grow. So when you have sample that is bigger than certain size, then mycelium wouldn't grow inside because it doesn't have that much oxygen. So it's not really that like you give it more time, it wouldn't grow more because then it just doesn't have oxygen and it doesn't grow. It's not dead then, it's usually dormant because it doesn't have enough like oxygen or water or nutrients to grow, so it just stops growing, and then you can add more humidity, for example, and then it would restart the growth. And that's the idea with these bio-welding components, where you first pre-grown components and then you put it together and then you have like enhanced humidity and then growing together into one structure. So I wouldn't say that time and scale are interconnected, but it's definitely connected with the amounts of nutrients that you're using, because if you have less nutrients, then mycelium needs more time to search for nutrients within the structure. So it grows slower because then like it's not that much nutrients. If you have more, then it grows right away. because it has energy to do it. Here, it's in the end it's life, so it doesn't want to give up on living. So if there are nutrients, it would look for it. So that takes more time. So it's a bit slower to grow samples with less nutrients than with more nutrients. But in that project, I'm not really taking time as important factor. Like even if it takes, I don't know, a couple of months to grow it, then why not, right? Like we might have a couple of months, we can send it ahead, or while people are there, they can just keep experimenting with that. But for now, it's usually like the samples that I'm having around like this size. The way how I'm doing it, I'm pre-growing mycelium with organic matter. So I'm calling that composition, mycelium and organic, as a biomass. So then I'm not able to say how much exactly mycelium I put, because I'm starting with pre-growing biomass. So I'm working with beechwood. So again, it's something that won't be available on Mars, but I'm not really looking into chemical composition. I kind of set on that worked, so I'll go with that because I just want to explore this mechanical structural properties of that. So let's say I'm pre-growing it for a week, and then I'm having this organic matter of like mycelium pre-grown with beechwood. Then I'm mixing it, like I'm blending it, because then if you break mycelium threads, then they tend to grow stronger. And also when I blend it, it's easier to combine it with inorganic matter. So then I'm combining it with sand in certain percentage. I'm adding water, and then I put it into molds for now. And then it's like 1 or 2 weeks of growth, and then the drying time is longer. So with drying, the components are getting stronger. So it's around a couple of weeks, 4 weeks, let's say, of drying. So in the end, like creation of the components is, I don't know, a month, a bit more than a month. And then you would have to like put them together and then restart the growth. Here it's where it's a bit more challenging for now, because I hoped that I just increase humidity and they start growing. They really don't want to do that. I know they're alive, because if I cut out the piece and I put it on like agar plate, then they're growing. It's not that easy, not that straightforward to restart the growth. So yeah.
I have a few questions, and it's okay, and I understand if there are no answers specific for them. But what is the biggest structure that you were able to create with the 2-week experiment that you had?
So I don't remember the dimensions, but it was around like 30 centimeters tall and like 15 centimeters diameter.
Yeah. Okay.
But also it wasn't the strongest. Like a bit smaller structure was stronger, and then much smaller was again super weak because my mycelium didn't want to grow, and I don't really know why. Like maybe the lack of oxygen. I really don't know. So there is a lot of unknowns working with biology, especially not coming from like biological background. And I'm asking my mycelium like, what do you need to grow? But yeah, that was like the biggest one. But I'm not working now with this size because it wasn't the strongest that I had. So I'm working with like around 20. So not very big, but.
So I do understand that there's a difference between the addition of nutrients in bioengineering the mycelium. Like both help in a different way. One is external factor, I guess, like when you're adding nutrients to it. Just in my basic knowledge, it's like similar probably to adding nutrients to an indoor plant. But there's also bioengineering the mycelium so that it behaves differently. Are you working in the pure form, or is it engineered, or what do you think that would need to happen?
Yeah, I'm not working with bioengineering at all. So the bioengineering part is more for me like a rationale, or as we were talking at the very beginning, like you have all of these ideas what it could do, but it stays for now in this realm of idea of like it can perform these functions, it can like provide radiation protection, it can all of the things that you could imagine. Probably half of it or more, it's not possible, but then there are things that are possible, like you can bioengineer Bacillus subtilis and then it performs specific functions. I'm not touching that area like through experiments. It's more like it stays in the rationale, and it's more like next steps. So if we know that, like if I'll manage to have this structural system that can be kept alive and doesn't digest the structural matter because its sun provides the structural matter, then even for terrestrial application, it provides, like it enables further research into living structures, because then mycelium can be kept alive, and then you can experiment with like engineering it towards different functions, but I'm not, I'm not touching that area. It's more like an idea.
Okay, so you're working with a pure form.
Pure form.
How do you get mycelium?
You can go to the forest and just scrap a little bit. You can buy mushrooms. Like when it was COVID and I didn't have access to any labs, I literally went to Tesco and I bought like specific species of mushroom, because the mushrooms that I'm working with, Ganoderma lucidium, it's edible mushroom. It has like really good inflammation properties. It's really good for you. I was never brave enough to eat like mushrooms from my experiments, because sometimes I have fruiting bodies. It's not desirable, you don't want that, but sometimes I have it. I wouldn't eat that. Yeah. But yeah, technically you can even buy it from Tesco. But like for specific experiments, like biological experiments, there's just a website, Mycelia, that I'm using. I don't know if I'm advertising here. And they just send you like this mycelium pre-grown on millet, and it's usually for farmers and like for actually growing mushrooms. But if you keep the conditions correct, then you keep not having fruiting bodies. It's like the CO2 levels and oxygen levels, and then you just have mycelium repopulating. The really cool thing is that you can buy it once, and then it lasts for the whole project, because you just repopulate it. The way I'm doing it, I'm doing agar plates on Petri dishes. I'm just putting, little piece of mycelium, it grows, and then after like 2 months, I'm making new agar plates with like a little piece of mycelium, so it keeps growing, and I'm having more material and new mycelium. I don't have to buy it again.
That's good. That's a really unfortunate business for them. Yeah. Have to tell you, okay, so I'm imagining. So at the beginning, you mentioned that it would be an inflatable, deployable habitat. Is it like going to be in my head? I'm trying to just visualize it. But is it going to be like a 2-layer inflatable, and then in the layer in the middle will be the mycelium? Is this how
yeah, so that's NASA approach with inflatable, and I'm not sure how many layers, because there's probably like, layers for water transportation, air transportation, oxygen, things like that. So I'm not sure how many layers exactly, but that the idea is that mycelium is inside. So from the inside of the habitat, you don't have direct connection with mycelium. From the outside, you don't have direct connection. In the long run, it would be cool to have direct connection from the inside, because then again, like this haptic surfaces, for example, it's mycelium can be really nice. It can be like this fluffy, soft surface that could be really good for like psychological comfort. But in the current state of the research, it's completely enclosed in this compartment. But in my research, I don't have inflatable. I'm just having the bricks. Let's say.
That's interesting. So what are your next steps?
So my next step is trying to find the proper optimal geometry for the components, and I'm looking into 3 types of processes, 3 types of parameters, and it's like iterative loop, iterative process, where I'm looking into assembly properties. So based on literature review and other projects, self-assembly structures, space filling structures, I'm looking like which geometry could be cool for dropping or like pushing, and then it assembles by itself. So that's first process. The other one is biological growth. So by growing my samples, I'm learning a lot of things, like size, the maximum size of the sample, or for bio-welding, it has to be increased surface to surface area, so the samples actually can bio-weld. Because for example, for aggregate systems, they very often base on point of contact. So you have like the spiky structures that are touching each other into one point, but that's not good for bio-welding, because you want to have surface to surface. So that's another like set of parameters that I'm trying to implement into the design of the component. And then the last one is fabrication properties. So, and that's also like kind of on 2 different time frames of the project, because right now when I'm working in the lab and in the workshop with drawing chamber, fabrication properties are very much related to what I can physically do in the space that I have, in 3D printers that I have, in materials that I have. So they're about like what's possible to do for me, but then in the long run, I also have to think of like what would be possible to do on Mars. So for example, here I can 3D print 100 molds and make 100 samples where each sample has one mold, but we don't want that for Mars. We want to minimize any other materials that you're using. So what could be the fabrication system that enables you to create, I don't know, multiple samples without using much external materials? So these three sets of parameters I'm trying to, or processes I'm trying to parameterize and like change into the things, the findings from my research I'm trying to change into implicit actions and put it in the like parameterized computational system to give me, like, I'm running the simulations on how the specific components assemble in lower gravity environment. I'm evaluating that, and then I'm deciding if it's something that I want to try to actually create and grow. And then on each step of this iterative process, I'm getting new parameters that I can feed to the system. So hopefully I find it
sounds
shaped.
like a lot of work.
It is a lot of work. I'm not sure what I'll be by the end of my PhD. I hope I'll have the like a cool shape that I can grow and I can make like a prototype that, you know, will grow in together, but we'll see.
And the software that you're using for the simulations, something that is you adopted or you developed?
No. So I adopted. So I'm like for the geometry of the component, I'm using Grasshopper with Rhino, and then for the simulations, I'm using. I started with Cinema 4D because you can like do cool simulations there, but it's not completely like accurately physically. So I'm looking into Houdini, but it's super complex. So I'm still like building the simulation system to see like what could work best and.
And when is your PhD due?
I hope to finish by March. So
oh, that's soon.
I mean, yeah, okay. A little bit less than a year.
Okay,
a bit less.
That's great. And your project is now your own research for your PhD. Is there collaboration with other entities right now?
So we're like still collaborating with NASA. So like I'm running this bi-weekly NASA micro-architecture NASA meetings where we're making sure that our objectives of what we're working on kind of meet in the same point
aligned.
For like the NIAC review. So my project is a part of NASA NIAC, but like I'm not like, you know, it's separate leg kind of, but yeah, it has to be in alignment. So it brings something to their research as well.
Yeah, I mean collaboration is always great. And okay, guess we're good.
Yeah.
Thank you so much for being here. I really enjoyed the conversation. I will put all the links in the description, and looking forward to having another conversation in March, hopefully.
Nice. Thank you so much for having me, Tana. It was really amazing.
Thanks.
It's always nice to talk about the research and exchange these ideas. So thanks a lot.